What's the difference between a comet and an asteroid? And what is the world record for the deepest scuba dive? This is Science at 6 with Cambridge Science Centre. My name is Joanne and I am this week's presenter in the centre. I hope you're all ready for some more science, technology, engineering and maths fun. You can try all the home activities from previous episodes and more at CSC Online, as well as any new ones from today's show. And finally, don't forget you can email your questions and activities to openupscience@cambridgesciencecentre.org or tag us on social media. As I'm sure you'll remember, last week's theme was Over the Moon. We asked you to try the Impact Crater Challenge. Who made a crater this big? This big? I'm sure you all did brilliantly well. Excellent job, everyone. And as you can see, I have my very own moon surface here, along with some asteroids that will impact the surface. My moon surface is made of 2 layers of sand, a base layer about 2 centimetres deep, and another layer of coloured sand on the top. Hopefully, when I drop my asteroids onto the lunar surface, we'll be able to see the craters that they make. So as this is a scientific experiment, I've weighed each of my asteroids. The ping pong ball is about 2 grams, the golf ball weighed about 40 grams, and this ball weighed 60 grams. I'm going to drop each of the balls from the same height, about 30 centimetres, and then we can measure the size and depth of the craters that they make. So I'm going to start with the ping pong ball. Here we go, and drop. Not much of a crater there at all. There's a tiny dent in the corner here, and that is about 2 centimetres. So let's try our heavier golf ball. This weighed about 40 grams. We definitely saw a difference in the crater that one made. It's gone deeper, and I think that's about a 3.5 centimetre crater. So finally, we're going to try our heaviest ball at 60 grams. Ready, and drop. I hope you noticed that made a bit of a bigger impact on the surface. It's about the same size as our golf ball, but it's a bit deeper. So that's how we completed our Impact Crater Challenge. It may surprise you to learn that as well as the moon, the Earth gets some rocky objects smashing into it from time to time. If you remember from episode 4, it's thought that an asteroid impact on Earth brought about the extinction of the dinosaurs. The largest impact crater in the world is called Vredefort crater in South Africa. It has a diameter of a whopping 190 miles. Imagine the size of the asteroid and the speed that must have been going. But how do I know it was an asteroid and not a meteor or a comet? What's the difference anyway? Well, asteroids, sometimes known as minor planets, are made of rock and orbit the sun. Comets also orbit the sun, but they're made of ice and dust and not rock. Meteoroids are small pieces of asteroids or comets that have broken off, and these are known as meteors when they enter our atmosphere before hitting the surface of the Earth, often creating beautiful meteor showers in the sky. Now, let's take a look at some of the great over-the-moon related questions you at home have been sending in.
Hi, my name is Mia and I'm going to be answering some of the questions that you've sent in this week. Our first question comes from Theo, age 7, who asks, could people live on the moon? That's a great question, Theo, and although it'd be really cool to live on the moon, it may be a bit tricky. One of the main problems is that the moon has basically no atmosphere. This means there'll be no air for us to breathe. So to survive on the moon, we would have to always be in a special spacesuit or an airtight moon building. Because there's no atmosphere to trap in the heat, a day in the moon can reach 125 degrees Celsius, and at night it can drop down to a chilly minus 173 degrees Celsius. These moon days and nights last around 14 Earth days each. To live on the moon, our special spacesuits would have to be able to keep our temperatures nice and stable when it's boiling outside in the day and freezing at night. All in all, I think it's probably a better bet to stay living on Earth. Next, our question comes from Jess, age 10, who asks, why does the moon affect the tides? Well, that is a fantastic question, Jess, and the answer is actually quite a complicated one. First of all, what are tides? Well, tides are the rise and fall of the oceans throughout the day. When the sea level is high, we call it high tide, and when it's low, we call it low tide. And we get 2 high tides and 2 low tides every day. The moon causes the tides because of gravity. Gravity is a force that pulls things towards the centre of an object. So, if I throw this ball up, it will fall back down. That is because the Earth's gravity is pulling it back down. The moon has a gravity of its own, which pulls things towards it, including the ocean. The moon is smaller than the Earth and much further away, so its gravity to us is much weaker, and we don't normally notice it, but we can see its effects in the oceans. So say this is the moon and this is the Earth. The closer you are to something, the stronger you feel its force of gravity. So the moon pulls on the oceans on this side of the Earth, making it rise. Now you may remember I said we get 2 high tides and 2 low tides a day, but at the moment we only have 1 high tide. And this is where it gets a bit more complicated. So, the Earth is spinning on its axes really, really fast, about 1,000 miles an hour. If anyone's ever been on a roundabout, you might have noticed that as you spin faster and faster, you have to hold on tighter and tighter to stop yourself getting thrown off. Now this is because when you're spinning, you experience a force called the centrifugal force, which pushes you outwards. The Earth is spinning, so the Earth experiences a centrifugal force, pushing things outwards. On the side closest to the moon's gravity pulls on the oceans, creating one bulge. But the further away from something you are, the weaker its force of gravity is. This means on the other side of the Earth, the moon's gravity is weaker, and the centrifugal force now wins, pushing the oceans out, creating another bulge. As we on the Earth spin through its rotation 1 time a day, we go through each of these bulges on the Earth, experiencing 2 high tides. Now, great questions everyone. Keep on sending your results and questions to openupscience@cambridgesciencecentre.org or on social media, and you may see them featured next week.
Great questions, everyone. Now let's leave the moon behind. Let's dive into our wonderful and often surprising oceans as we say hello to Mario and his Cartesian Diver.
Hello, my name is Mario and I'm one of the science communicators here at Cambridge Science Centre. Today we'll be making ourselves a Cartesian Diver. What you'll need is a pair of scissors, a bendy straw, some blue tack or plasticine, a glass of water, and preferably a 2-litre bottle filled with water almost to the top. And you'll need the lid for it as well. First, you need to take your bendy straw and carefully bend it over so it forms a nice curve. You can then use your scissors to cut it a little bit shorter so both sides of your straw are of equal length. You'll be left with a U or V-shaped piece. Once you've done that, you can then take your piece of plasticine and wrap it around your straw, like so. Then you'll need to take your Cartesian Diver and pop it inside a glass just to make sure that it will float, whether just above the surface or just below. There we go. Perfect. So once you've got yourself a floating Cartesian Diver, it is a little bit fiddly sometimes, so sometimes you do need to remove a bit of your weight or add a little bit more just to get it to be perfectly just below the surface like I've got it here. So now we've got our diver that floats in our glass of water, we're going to transfer our diver into our bottle. So just gently put it inside your bottle and it should hopefully float quite close to the surface. So then make sure you put your lid on nice and tight. But how do we get our diver, who is currently floating around near the surface, to dive? You then now need to squeeze your bottle very gently. Squeeze and release. Amazing! What's happening inside the bottle to make our Cartesian diver dive? To do that, I'm going to show you something to watch closely as I blow into this straw. You may have noticed that as I blew into the straw, the bubbles produced floated to the top. This is because air is a lot less dense than water. The tiny particles that make up air are way further apart than the particles that make up water, with lots of empty space between them. The air particles move around like crazy, whereas in the water, they're quite tightly packed together with not much room in between them. Air is trapped inside the straw of our diver, making it float. When we squeeze the bottle, we increase the pressure inside the bottle. Some water gets pushed into the straw and shrinks or compresses the air bubble that's inside the straw, pushing the air particles a lot closer together. This reduces the bubble's buoyant force, the force sending it upwards, until it's unable to support the weight of our diver. So the diver starts to sink. But when we release the pressure, the compressed air bubble pushes back. It pushes outwards, forcing the water out of the straw, resulting in the diver rising back to the surface. An object less dense than water will float, whereas an object denser than water will sink. But what exactly is density? Density is how much something weighs compared to its size. When the diver is floating, its density is less than that of water. The pressure when we squeeze the bottle reduces the volume of the air bubble. This results in the total volume of the diver decreasing, so its density increases and therefore it sinks.
Thank you, Mario. And thank you, René Descartes, the 17th century philosopher who this experiment was named after. If you have a go at home and you'd like to share your work with us, just drop us an email with any pictures to openupscience@cambridgesciencecentre.org or tag us on social media. Now, humans can swim pretty deep into the ocean nowadays. All you need is a tank and some flippers, right? Well, not exactly. The deeper into the ocean you go, the darker it gets and the colder it gets, and the more pressure there is pressing in on you. Less and less sunlight penetrates the deeper you go, meaning it's really dark and really cold. But how do we explain the pressure? Water pressure is the result of all the water above pushing down on the water below. And the deeper you go in the water, the more water there is on top of you. So there's a greater weight of water pushing down on you, and therefore a higher pressure. There are some things we can use to help us though. Scuba gear helps you to breathe underwater. Unlike our Cartesian diver, a scuba set would allow you to breathe just like you would on land, without the extra pressure forcing air or water into your lungs. You might also want a wet or a dry suit to keep you warm, and you'll probably need a waterproof torch so that you can see around. The world record for the deepest scuba dive is held by Ahmed Gabr, who dived an amazing 332.35 metres. But nature is always one step ahead, and sperm whales can dive to depths of over 1,000 metres. The massive pressure means that their lungs compress down to about 1% of their size at the surface, and this changes their buoyancy, allowing them to stay at such great depth. Fantastic, isn't it? Well, diving is a great way to learn about the ocean, especially for studying life underwater. And my friend Alex spoke to Kiran Bhandari, who is a PhD student at Bangor University. He wanted to find out a little bit more about sea life and how we research it.
Hello, Kiran. Thank you for joining me today. Could you first start by introducing yourself and telling us a little bit about what you do?
Okay, so my name's Kiran Bhandari, and at present I am a PhD student at Bangor University, conducting research on crab and lobster fisheries and how fishing for those particular animals might affect their long-term survivability.
What is it about marine biology that makes it important to you?
I grew up in a remote village in the middle of Oxfordshire, so actually going to the sea and stuff like that was a bit of a treat really for me when I was a child. So I learned to dive when I quite at a young age, from 12. A lot of the documentaries that are around, sort of like the early 2000s, like Blue Planet and some of the Discovery Channel programs, really inspired me as well. I've seen these amazing animals which you find living in the sea on TV. Kind of made me thought, ooh, I want to see more of those things. And what can I do to see those things for real and up close? So that was kind of the reason why I got into it and why marine biology kind of is special to me really. The reason why I picked crustacean fisheries in particular was because before I did this PhD, I was working for the Marine Management Organisation as an enforcement officer. To put it simply, I was a fish policeman. That's probably the best way of describing it. So essentially, I monitored the fishermen in and around sort of the Yorkshire coast area. With Scarborough being quite a small port, it was very, very much dominated by crustaceans, mostly crab and lobster. So that's actually what sort of sparked my interest in them.
Say with the PhD or maybe the enforcement role that you had, do mostly all the people that you've worked with or are working with have a similar background to you?
No, actually. Well, in particular, if I point to the marine enforcement role, I was actually the only person in my office who had any sort of scientific background. Compared to what it is now, I've got a much more similar kind of background compared to a lot of people that I know are also doing oceans. However, the level of experience that people have got, however, is very different.
Yeah, that's great. That's really interesting. So final question. Could you talk about someone who inspires you and a little bit about why?
Well, two people I admire in particular. One of them is the late Canadian filmmaker Rob Stewart. Because in particular, it's because of one documentary he made called Sharkwater. It's because he wasn't afraid to really show things for what they were. He didn't try and sugarcoat it or try to hide anything. So another person I really admire is Paul Watson, who is the creator of this organization called Sea Shepherd. He's a person who hasn't been afraid to kind of get down and actually try and expose the kind of really unpleasant, almost illegal aspects of fishing as well.
That's really interesting, yeah. Thank you very much, Kiran. That was great, and really appreciate you coming on for this interview.
No problem. It's been a pleasure speaking to you.
Great. Thank you, Kiran and Alex. That was really interesting. So, you might have guessed that this week we would like you to explore ocean life and try out our plankton challenge. So far, we as humans have only really explored about 5% of the world's oceans, so there may be many more creatures to discover in the watery depth. So as always, simply check the link below for our activities and a link to the information for the plankton challenge. Don't forget to send us your questions and pictures of your work, and we'll take a look at some next Monday on Science at 6. Goodbye, and thank you for watching. See you next time.